Hello, this is Coach Meinbauer for AP PreCalculus. We're going to go over 1.11. There's two parts of it. One's binomial theorem. I'm not going to do that one today. What we're going to do is our equivalent representations of polynomial and rational functions. So we're going to talk about some more stuff with slant asymptotes, where those come from, and really just talk about all the asymptotes involved with a rational function and kind of start to put everything together here that we've been learning in previous parts. Okay, so recall from one of our previous lessons, we talked about a slant asymptote existing, which, by the way, is pictured below. You can see that slant asymptote has a slope of, if I'm just kind of guessing and counting here, it looks like it's got a slope of 1, this dotted line, up 1, rise 1. So that's got a slant asymptote of 1, and you can see how the end behavior is going to positive infinity to the right, left end behavior is going to negative infinity. So that slant asymptote is going to occur when we have a power on top be 1 higher than the power on the bottom. And again, this is for all rational functions. Reminder, rational functions is when we have a polynomial divided by a polynomial. Okay, so to find the equation of the asymptote, I kind of showed you a shorthanded way before, but let's get technical here. We have to use long division to find the slant asymptote. So we're going to do some polynomial long division. Before I do that long division, I'm going to show you how we used to do long division right here. So here is our old method of just numeric long division. And that's when we would take this 21 right here, put it on the outside, and we divide 676. Okay, so your first step is to figure out how many 21s go into 676. Now we kind of break it down. Since we have 2 digits for 21, we'll look at the first 2 digits here for 676, which is going to be, I say first 2 digits, I mean the 6 and the 7 on the front end. How many 21s go into 67? 3. Okay. And then we multiply to get 61, and then we subtract. So really, we divide, we multiply, we subtract, and then we bring down this 6 right there at the end. So 66, and 21 goes into 66 how many times? 3 again. Is it a complete 3? No, there's actually going to be some, oh boy, dark again. We're actually going to have a remainder here. Subtract that, and we're going to have 3 left over, so we used to put R3 for remainder 3. Okay, so the quotient here is going to be 33. The remainder is 3. How do we write this as an answer? This is actually going to be 33. Okay, and 3 21sts. So we write it. No, I lied. It's been a long time. All right. I lied. It's going to be 33 and then 3 676. I'll get it right eventually. All right. So that's what that looks like, old school. Now, new school is going to be, well, it's not really new school. We really do the same thing, but we're using polynomials. So if you notice, our numbers here kind of look very similar. So we're going to divide 2x plus 1 on the outside, 6x squared plus 7x plus 6. And we're going to see how many 2x's. We're going to look at just the first, the larger power of the two. How many 2x's go into 6x squared? 3x's go in there. So 3x, I'll put the 3x over the x column. Let's just call it that. Multiply that back through. We're going to get 6x squared plus 3x. Just like we did in the other one, we multiplied. Now we're going to subtract. Now be careful. I'm going to subtract everything, not just the first part. So I subtract the 6x squared. That's gone. That's 0. And I do 7x minus 3x. I'm going to get 4x. And I'm going to bring down this 6. Okay. Now for this one right here, we have 2x goes into 4x how many times? 2. So it goes in 2 times. Multiply that back through. I'm going to get 4x plus 2. Subtract that. I'm going to get 4x minus 4x is 0. 6 minus 2 is 4. So I have left with a remainder of 4. So the quotient is 3x plus 2. The remainder is 4. How do you write this? Well, we have 3x plus 2 plus 4 over, oh man, I'm thinking I had a mistake on the last one too. I clearly did not prepare. This is going to be, it should be actually over this 2x plus 3. Or sorry, 2x plus 1. Which means that this one's wrong over here, which I should have known that at the start. It's 3 over 21. Which is 1/7. I was right the first time. Yeah, I can explain how I knew that was wrong, because I hate this division symbol, by the way. It really annoys the living daylights out of me. Anytime you go like any of those like TikTok videos and they're like, oh, what's the real answer? And they always show this division whenever they have to go through PEMDAS. I hate it. This is the same thing as saying 676 over 21. Okay, so then we're over 20, everything's over 21. Just like this long division thing is saying that this 2x plus 1's on the bottom. Okay, so that's why when I write my answer, that 2x plus 1 is going to stay on the bottom. Yeah, I should have known that over there. Oh, well. Everybody makes mistakes. That's what Hannah Montana told me. Okay, example 1 here. Let h of x equal. This looks kind of sort of familiar, by the way. It looks very similar to this problem. But use long division to find the equation for the slant asymptote. What's important back over here for the long division is the quotient is my slant asymptote. So my slant for this one would be y equals 3x plus 2. In previous videos, we went over this kind of the shorter way, and that would just give us only the slope for the slant asymptote. It didn't give us the actual slant asymptote, but it gave us the slope. But for this, I want the actual slant asymptote if it's getting pushed up or down from the origin. So in this one right here, so you go ahead and use long division. So we're going to do 2x plus 1 divided by 6x squared plus x plus 5. If you want to give this one a try, you are more than free to pause the video and try it out on your own. And we're back. 2x goes into 6x squared 3x times. So multiply that back through. We're going to get 6x squared plus 3x. But we are going to subtract this. Be careful here. We're going to get 0. X minus 3x is negative 2x. Drop down that plus 5. Okay. 2x goes into negative 2x negative 1 times. So we're going to get negative 2x minus 1. We multiply it back through. We subtract all these negatives. Kind of gets weird, but we're going to get 0 on the front here. We're going to get 5 minus negative 1, which is really a positive 6. So this equation here of this rational function becomes 3x minus 1 plus 6 over 2x plus 1. What we only care about is this 3x minus 1 part. That gives us our slant asymptote of 3x minus 1. Okay, so we just look at the big part, the quotient, if you will. All right, let's try to make no more mistakes. No promises. Okay, for this first one right here, example 2, we're going to find all of these equations of the asymptote. So real quick note here, if you have a horizontal asymptote, there is no slant. So you can't have an horizontal and a slant asymptote. It's not possible. Okay, here we go. G of x on the top. I think it's easiest if we look at this as a factored form. That way we can pick out what the holes are, what the vertical asymptotes are, and then we can pick out our slant asymptote by using the OG form, the one where we're not factored at all. So if I were to factor this, and hey, look, it's even asking for the factored form. It looks like I'd take out an x on the top. So I'm going to rewrite g of x as x, and then x squared plus 4x minus 12, which does factor, by the way, all over bottom factors as 6 and 1. Okay, so our factored form for g of x, that one step left, I'll just put the answer over here. That line couldn't have been any wavier. Okay, the top is going to be x, and then we're going to get that factors as 6 and 2, so plus 6 minus 2. Okay, so that's the factored form. If you notice here, those x plus 6's are going to cancel out. That's not going to be involved in anything that we do. So let's go ahead and find a vertical asymptote. It's going to be at x equals -1. Take note here. X equals -6 is a whole. Okay, I mentioned that because the top and bottom have the same factors. Horizontal asymptote, it's much easier to look at our non-factored form. If we notice here that we are bigger on top in terms of the degree by 1, so I'm going to have a slant asymptote. If I want to find the actual equation of that slant asymptote, I need to do some long division. So here we go. I'm going to do x squared plus 7x plus 6. What's nice about those long divisions is I just need to go far enough until I'm done with my constant term. Okay, x squared goes into x times, multiply that all the way through, and we are going to subtract everything. X cubed minus x cubed gone. 4 minus 7x cubed is -3x, x squared. 4x squared over 7x squared. -12 minus 6 is going to be a minus 18x. Okay. I just need to do this one more time because I got my constant term, and then I am done. So x squared goes to -3x squared, -3 times. You really can be done right there. There's no reason to go any further. This is my slant asymptote. Because once I get that constant term, I'm done, and there is none for horizontal. Okay. Let's move on. Ooh, this wants me to sketch, so we're going to put everything together here. All right. We got it. Here we go. Write an equation for k of x in factored form. So real quick, the top does factor as x minus 4 plus 3. Bottom factors as, I can take out an x, by the way. So I'm left with x squared plus x minus 20. I'll put my factored form over here. So the top is x minus 4, x plus 3. Bottom is going to be x, and then I got my double bubble. I'm going to get x and x. What multiplies to 20 and adds to 4. I got a 4 and a 5. Plus 5 minus 4. Those minus 4s will cancel out. So we're going to have a whole at 4. So find any x values where k of x has a whole. X equals 4. And I'll kind of I'll use my red marker here. Cancel those out because those aren't that important right now. Okay, that's where my whole is. Find any zeros. That's the remaining values on the numerator. So I'm going to get x equals -3. Find the vertical asymptotes. I have 2 of them. I have x equals 0 and I have x equals -5. That's just setting each of those factors in the bottom equal to 0. Find any slant asymptotes or horizontal asymptotes. Well, what's kind of nice about this is I have bigger on top, smaller on bottom. So I have a horizontal asymptote of y equals 0. No long division because the power on the bottom is larger. I'll find the domain after I sketch. I think that's a little bit easier to do. So here we go. I'm going to take all my information I have right here and draw it on over here. So I have a zeros at -3, which is right here. I have a whole at 4. I'll get to that part in just a second. I have vertical asymptotes at 0 and at -5. 1, 2, 3, 4, 5. Okay. I have a horizontal asymptote at 0. You might be saying to yourself, well, that point goes through the horizontal asymptote. Coach, how is that possible? You can go through horizontal asymptotes. Those only refer to the end behavior, not the middle behavior. So you can certainly go through that. What else we got here? I think we've got everything except for the whole. So the whole is at x equals 4. Where is that on my graph? If I were to just plug in a 4 here into my new k, so let's say that I plug a 4 in, I'm going to get 4 plus 3 on top over 4 times 4 plus 5. That's giving you my height of my hole, which is 7 over, me and math don't do well, 36. So like it's just slightly above. Okay. So my domain here is going to be everything except for where my hole is and where my vertical asymptote is. So it's going to go from negative infinity until negative 5. I'll use unions because we're talking about domain specifically, so unions are okay. So from negative 5 to 0, from 0 to 4, from 4 to infinity. Only thing left to do is just to sketch this. There's not much here. Don't fret about it too much. All we're going to do is just plug in some points, see what matches up and what's going on here. We can kind of look at our end behaviors near our vertical asymptotes. It's really the best way I would do it. So let's find values that are close to my vertical asymptote. So I'm looking at 0 from the right. I'm going to plug in I'll just plug in a 1. Okay, that'll give me enough if it's going to be at negative infinity or positive infinity. If I plug a 1 into this k value right here, I'm going to get positive on top, positive on bottom. I'm actually positive. So this is going to come through to my hole somewhere. It's just a sketch, so it's not perfect. Okay. If I look at 0 from the left, that's going to be a negative 1. If I plug in a negative 1 on top, I'm going to get positive. On the bottom, I'm actually going to get negative. If you're wondering why, just plug it in yourself. And I know I have to go through this 0, so it makes sense that I'm going to be hugging that asymptote right there. You can always check it too. Plug in a number that's near negative 5 to the right, like negative 4. You'll see that that's going to be positive. And then let's go ahead and plug in a value that is larger than 5. Sorry, negative 5. That's smaller than negative 5, so like negative 6. Plug in a negative 6. I'm going to get negative over negative over negative. Yeah, so we're going to get end behavior that looks like this. Okay, so don't fret at the sketching so much. That's not the focus here. The focus is here. We're just going to put everything together, and we can show you that we can sketch. We're capable of doing it, but that's not really what this whole point is. We're really just trying to put together what a rational function is. We can graph it. We're capable of doing it, but we're not going to expect you to do it. So that wraps up my video here. Please like and subscribe.